Yes, friends. Now it's time for our other advanced topics about threads. Now, our first topic is interrupting a thread. The basic idea here is this. We have two separate threads. In the structure you see on the screen right now, we have a main thread. Here, thread.currentThread is already our main thread, meaning our existing thread. The new thread here, on the other hand, is another thread derived from the existing thread, meaning it's running somewhere else. So, what's happening here? What's going on here? The logic here is as follows. Normally, our code runs from top to bottom. We create a new thread. Here, first, we get the current thread, that is, the main thread. Then, we create a new thread and make this thread continue a certain process. After that, we have a loop. In this loop, it checks the following. The loop continues as long as the counter is less than 1 million. Here, we also have a sleep method. The basic logic here is this. The counter, that is, while checking this counter, it waits for 1 second and then checks again. So, the inside runs once every second. Now, in the thread above, a loop has been created up to 1 million. This loop is running. After this is finished, look, it interrupts the main thread I defined here. It says, hey, my job is done. If my job is done, then inside this loop, in other words, it's actually talking about this main thread. It says, you can also interrupt this main thread. The basic logic here is this. If you're going to perform more than one operation at the same time, you're doing certain tasks sequentially. Now, let's say one takes 1 second, the other takes 1.5 seconds. One takes 2 seconds. Let's say we have a bunch of threads like this. A lot of work to do. Now, these are waiting for each other. They're waiting for each other to finish. I mean, we created threads so they wouldn't have to wait for each other and could work independently. But think about it like this, guys. There are tasks that need to be completed in total. For example, I finish my work in 1 second, but my friend finishes in 1.5 seconds. Another friend finishes in 2 seconds. So what do I need to do now? I need to wait for the others. I finished my work in 1 second. The other one finishes in 1.5 or 2 seconds. Normally, that's the standard. So I wait too. But there's also this situation. If my friends, instead of finishing in 1.5 or 2 seconds, the one who usually finishes in 1.5 finishes in 1.1 seconds, and the other one, instead of finishing in 2, finishes in 1.5. Now, in this case, they need to stop working or warn me. Like, we're done. Like, you should finish up too. So, certain threads can end other threads like this, guys. Of course, that's if you hand over that thread to the other one. They can stop each other in this way, in a chain. Of course, there are different methods, different solutions. This is a whole different thing. But the basic idea here is that while a thread is running, you can terminate that thread, guys. So you can interrupt its execution halfway. What we're doing here is, as an example, the extra thread that's created interrupts the main thread's execution. If you pay attention here, there's a problem with the thread. Look, the thread gets interrupted, and when it does, it throws an interrupted exception. We're already catching that here. We notify about it, and then the application goes down, guys. That's how the system works. Let's continue. Another thing we have is the single executor, guys. This is a structure we can use for certain specific tasks. The basic idea here is that, just like we use threads, we use this to easily manage these tasks through a single executor. Here, of course, when we execute these tasks, that is, runnable tasks, we can manage them here and have them perform operations one after another. we can start all of them at the same time. We can terminate this executor service whenever we want. So, think of it like this. Let's say you gave 3 tasks to the executor service here, and you want all the others to finish as soon as any one of these tasks is completed. Here, friends, if you use shutdown, when one of them finishes, the system says, "I'm done." So, when you call shutdown, all the tasks associated with the executor service are terminated, friends. They all finish. Here, to explain the logic of this structure, I'm giving a basic example, friends. Our main point here is this. First of all, when we create an executor service, the main logic at this point in the system is as follows. You can shut down and terminate these, but once the tasks have started running, for example, after you have started the tasks you need to give to the executor service, you can no longer submit new tasks here. After that, when all the main operations are finished, the system is terminated and all the tasks are completed. Let's look at the topic of waiting for results. Here, basically, all the threads would perform the tasks assigned to them independently, and after completing these tasks, the processes would end. But do our runnable methods running on these threads actually finish when the process is complete? In other words, do they cause any problems? For example, was there a deadlock somewhere, or could it have ended for some other reason? That is, the task might have been terminated somehow. So, a problem might have occurred, or it might have completed its task without any issues. Now, here we need to pay attention to this. Sometimes, we need to understand what is happening on the threads we are running. Because depending on what happens there, we might continue with a certain flow, or decide what to do next. That's why we expect to get something back as a result of the operation performed. So, our single executor service from earlier will actually do this. It will take the tasks that are given to it. It will return information to us about how these tasks ended. So, where do I use this? For example, there are some queries I need to run one after another. At the same time, I send requests to 4 different points, to 4 different databases, and as a result of these requests, I get some data, and from that data, I extract the IDs. Now, normally, this is how I would do it. I would do it sequentially from top to bottom within the main thread. When finishes, next. When finishes, next. But this is a clunky system. Because the second query doesn't get sent until the first one finishes its job, the third doesn't start until the second is done, and the fourth waits for the third. But what if I sent all of these requests at once? I mean, connected them to threads and sent the requests all at the same time, and then continued after these processes finished in order. How about that? Isn't that great? Normally, if this process takes 4 seconds when I do it on the main thread, when I do it with threads, it would take about 1, maybe 1.1 seconds at most. Can you see the difference? There's a huge difference between them. That's why it's really important to see the results of the threads we're running like this. Guys, here we also have a class called feature. This feature object makes our job easier. Guys, we can understand what's going on there through it. One of the important features in Java is functional interfaces. Guys, these functional interfaces, especially with lambda expressions, have really allowed us to have very nice usages and clean coding techniques. Here, too, we can handle our operation with an arrow function by using the callable interface. Here, the code becomes simpler rather than more complicated. And again, as a result of the operation done here, it gives us a feature as a result, and we can check its outcome accordingly. Guys, I especially recommend that you use this. Now, another important point is this. Scheduled tasks. Friends. Here, Scheduled tasks. Within applications, there may be tasks you want to perform at certain intervals or during specific time periods. For example, in my own application, I have applications that end at certain hours at specific time intervals. Let me put it this way. For example, I organize a competition. At the end of the day, or for some, at the end of the week, this competition needs to end, and after it ends, a series of processes need to be carried out in order. These are standard things. For example, I can schedule these like this, trigger them with a cron job, and that way, I don't have to deal with their integration at the end of the day or week. Or I create a competition. Of course, I keep these competitions in a database with their properties, and I schedule them there. My task manager listens to this database at certain intervals. For example, is a new competition going to be opened in this database? It sends an SMS to everyone who can participate in that competition. Or it sends a notification through the app. This way, it makes sure those people are informed about the competition. Or we can set up certain alarms. I can use these scheduled tasks to send SMS to administrators or partners who need to perform certain actions within the app, thanks to these alarms, friends. That's why it's a very useful feature. You definitely need to try these out in your applications. You really should be trying them. So, how do we use it? Again, if you pay attention, here you create a thread called single schedule executor. This thread executes the runnable task assigned to it. Notice that you can run this either with a runnable, or you can define it as a callable using an arrow function from a callable interface and run it that way. The basic idea here is this. First, you assign a task to it through the ScheduledExecutorService. Then, you specify how often this task should be repeated. And the interval here, for example, I've written 8 here. Is this 8 hours, seconds, days, months, or weeks? What is it, exactly? You need to specify this. Once you specify it, from the moment it starts, it keeps running continuously according to that time unit, and it has a very useful structure, guys. I definitely recommend you use this. Another topic is that when you define something in executed service, friends, the single executed service handles your tasks on a single thread, but our tasks aren't always like that. For example, you might need to do 10 tasks at the same time. A single thread won't be enough for 10 tasks, for instance. You need to have more than one thread. And maybe these threads need to run and finish at the same time. The tasks assigned to these threads. So, to manage things like this, you can define a thread pool and set the number of threads. In other words, you create a thread pool. Here, you say, for example, I have 20, 30, or 50 tasks. Create a pool of 50 threads. Add these tasks one by one, click, 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 in order. Then start them all. They all start at the same time and almost finish their tasks at the same time, wrapping up the operations, folks. But if you notice here, I've set the thread pool to 20. The thread pool can be larger, but by default, if you don't change anything, it will assign you 10 threads in the thread pool. But with Java 21, there were certain limitations and issues with these threads. Now, with Java 21, folks, there are no such limitations on threads. Because the concept we call virtual threads has come into play, now you can create as many threads as you want. Of course, when we say as many as you want, you need to use it in proportion to the CPU capacity of the computer you're working on. In other words, if you say you'll create unlimited threads, you could end up freezing your computer. So you need to be careful about that as well. Alright, now we've come to atomic classes. Guys, we're working with a completely customized structure outside of the normal flow. So, the concept of threads here means that we're stepping outside the normal flow of the main thread, and they're running in different locations and memory areas. Now, because of this, each thread has its own stack. Guys, they operate there. So, in this situation, they can run into problems when accessing certain data, in other words, when accessing specific data in the heap area. For example, you can't just use a primitive data type in more than one thread at the same time. In other words, you can't take a primitive data type from class A and use it with another thread in class B. And the reason for this, friends, is as follows. Threads have their own stack areas. A thread cannot access the stack area of another thread, so they can't access each other crosswise. Where can they access each other from? They can access each other from the heap area. Now, here's what you do in the heap area. Let's say you're in class A. In class B, a thread wants to access a value from class A. What does it do? It creates an object from class A and accesses it. However, when you think about creating and giving an object from class A to A, B, C, and D, a new drawback appears. All the threads are accessing the same object reference. When this happens, the conflicts I mentioned in previous lessons occur. One is increasing while another is decreasing. The data starts to become inconsistent. By using atomic class here, you're actually working around this issue. This ensures your values are as safe as possible. In other words, multiple threads can't access it at the same time. So what happens when a value is accessed or when someone tries to retrieve a value from it? It locks that value, friends. When the thread is done, another thread can access it. That's why using atomic classes is much more beneficial. In fact, you can't use a regular primitive data type within a thread, friends. It will already give you a warning that you can't use it. Here, I've given a direct example using atomic integer. You create an object of atomic integer with an initial value. Then here, it has its own methods, friends. When you call increment and get, it both retrieves the data and, before retrieving, what does it do? First, it increases the value, then it retrieves the data. Look, here it's increment and get, and here it's get and increment. In this case, it first retrieves the data, then increases the value. These are the ways you can use it, friends. Again, with methods like get and set, you can read the variable or change its value, friends. Now, our next topic is synchronized blocks, friends. What is this? What is a synchronized block? Again, it comes down to the same thing. You want to access a value within the class. When you want to access this value, whether it's a method or a variable inside an object you've created, these can be accessed by multiple threads at the same time, and this can lead to various problems, friends. That's precisely why, to ensure complete data consistency and its proper usage, it's much better to consistently use synchronized blocks, my friends. Break time equals 0.5s/. Here, by adding the volatile keyword to the variable, you can ensure that the variable is locked and accessed correctly, but that only helps you up to a certain point. After a certain point, you start to experience problems with that as well. But with synchronized blocks, operations generally run smoothly as much as possible. But is this safe, too? Guys, sometimes this isn't safe either. And here's why, friends. Now, the JVM is, after all, a virtual machine. The threads we create on this virtual machine are actually designed to virtualize the real environment. There's nothing there that's truly finalized like in a real environment, but there was an article published showing that, even if rarely, data inconsistencies can occur in test environments. So right now, the safest thing is actually the synchronized block, but even with this, There's still a very slim chance you might encounter such an issue, though it's very unlikely. Now, guys, sometimes we really feel the need to perform operations on lists. Especially in my own application, I have to use structures like lists, maps, sets, tree maps, and hash sets extensively, and when I manage these with threads, data inconsistencies can really reach a high level. Because normally, when you're working with just one user or maybe a few users, you rarely see any issues, but when tens of thousands or hundreds of thousands of users are accessing certain areas, using these collections, that's when you start trying to fetch data and problems arise. It pulls data from the database, processes it, sends it to threads, and so on. Here, due to the heavy processing load, you can really experience certain delays. These delays can come back to you as data inconsistency. To avoid these issues, within the concurrent API, we actually have special collections, what we can call concurrent collections, that are in a synchronized collection structure, like our lists. Thanks to these interfaces, we have structures that minimize the risk of data inconsistency and the problems that can arise when multiple threads access a list or a collection at the same time, friends. If you are going to use such structures, meaning if you are going to perform operations on lists with many threads, I strongly recommend that you use synchronized lists as much as possible. Otherwise, it can really be difficult to handle, friends. We've come to the end of this. This is truly a very tricky topic, friends. It's an advanced subject. You really need to work on this a lot. You need to move forward with lots of examples and read articles about these topics. Here, I provided information about the most striking and important parts. We wrote examples. I showed examples. You need to try these one by one and improve yourself a bit more.